Good morning, class, and welcome to another lecture in sustainable energy technology. Today, we will start our discussion on a different part of energy technology. We will look at the demand and the distribution side of energy technology and what unique technologies are required to make it possible to successfully integrate renewable energy systems into the electrical grid. Before going into some of the technologies that are required to successfully integrate renewable energy systems, we will discuss what are the main characteristics of energy or electrical demand and how traditional systems cater to the demand of electricity that happens throughout the day or throughout the year in a particular country or a city. So one of the key ideas is that electricity demand or energy demand is variable from one period of the day to another period of the day and is also variable between different seasons of the year. And it is essential that the electrical grid successfully caters to the variable demand, because if there is a demand-supply mismatch, then that means that there may be chances of grid overload or grid failure. For grid overload cases, you will have greater amount of electricity entering the system than leaving, creating large voltage fluctuations. And for grid failure, if the demand exceeds supply, then voltage may drop and that can lead to large-scale blackouts. Hence, demand-supply matching is a major aspect of grid maintenance and maintaining the quality of the electricity supply over 24/7 period. So first we will look at some of the aspects of variation in electricity demand. Variation in demand of electricity and energy. So we will look at a typical energy demand or electricity demand curve at location in summer and in winter. The specific curves basically discuss a specific city, which is San Antonio in Texas. This is an arid climate which is hot during summer and cold during winter. Okay. So San Antonio, Texas is a typical continental climate. It's a city which is extremely hot during the summer months and quite cold in the winter months. So in the Indian context, this will be like Delhi in India, which can become quite extremely hot in summer and reach quite low temperatures during the winter times. So for this city, the demand curve of electricity in summer and winter months looks something like this. Okay. So here is the power demand in megawatts. This is 5,000 megawatts. (4,000 megawatts, 3,000 megawatts, 2,000 megawatts, 1,000 megawatts, 0. And on this side is the hours of the day. So this is 0, 4, 8, 12, 16, 20, 24. This is hours of day. Okay. And first we will look at the energy demand on a weekday in summer. So this is summer weekday, and we can also plot the energy demand on a summer weekend. This is summer weekend. So here what we see here is there is a large peak in energy demand between 1200 hours to around 2000 hours, especially during the summer weekdays. High peak demand between 12 noon and 8 p.m. night. And this peak demand is associated with high air conditioning load in offices and homes. Okay. So clearly during the summer months, especially in the summer afternoons and early evenings, there is a large air conditioning load that creates a peak demand. In the late nights, for example, demand is low because other systems are off and air conditioning is also turns off. But during the afternoon times, there is a large peak demand due to the high AC load in office spaces, as well as in weekend there is a large AC load in the households that causes also a peak demand during this time, though the values are lower. So this impacts creates a peak load which is around 4000 megawatts, whereas the base load which is the kind of the mean load that is in the non-peak hours is around 3000 megawatts. So 1000 megawatt extra load can occur during the peak summer afternoons because of the extra air conditioning load. Similarly, if we look at a winter time, so winter in San Antonio is significantly cold. So you have again 0, 4, 8, 12, 16, 20, 24. We have 1000, 2000, 3000, 4000. Now in winter, loads are typically lower. However, you will see that there are two peaks. Okay. Similarly, in the weekends, the peaks are somewhat less prominent. So here the idea is there is a peak load here due to heating demand in office spaces. And here at late nights, there is heating demand at homes. So in winter, in the early morning between 8 am and 12 pm, because it's quite cold, the office spaces need to be heated for the workers. So that creates an excess peak load during this period in San Antonio. Similarly, when people return home after say 8 pm to up to 12 pm when they are active, there is also a significant heating demand in the homes, which creates a second peak here. So what we see here is based on the seasons and of course the time of day, there can be large variations on even the average power demand in a city. And any power generation system and grid system has to be able to cater to these demands in a successful manner. So let us discuss certain operating parameters of a power plant. Some of these we have come across before. I am just refreshing it so that we can use it in the next few lectures. So first is rated power or plate capacity. This is the nominal or designed for electric power a plant may produce. So this is basically the capacity that the manufacturer says the power plant is rated for. It's called the rated power or plate capacity. Okay. It's a nominal or designed for electrical power a plant may produce according to manufacturer certification. A second term is peak power. So a peak power is the maximum power that is, so it's firstly maximum power that is actually produced. So it's actually produced and is a few percentage points higher or lower than rated power. So peak power is the maximum power that is actually produced by a power plant during its operational duration, and it's usually a few percentage points either higher than rated power or lower than rated power. Okay. Then you have the definition of average power. So average power is the average of the power produced by the plant over the course of a year. From that we get something called availability factor. So availability factor, also called AF, is the fraction of time the plant is switched on and contribute to electrical power generation for the grid. So availability factor is the fraction of time over a given year that the plant is switched on and contribute to electrical power to the grid. Okay. So a power plant may be running for 24/7 throughout the year. Then its availability factor is 1. However, if a power plant is running for only say 6 months and is switched off for the other 6 months, its availability factor will be half, because it is on for half the year and closed for the other half of the year. Then we have something called the power operating factor. POF, and it is the ratio of total electricity generated by a power plant during a year to the total electricity it would have generated if it were to operate continuously at its rated power. So it's a ratio of the total electricity that is actually generated by the power plant to the total electricity it would have generated if it were operating continuously at its rated power output. Okay. So we can define these two terms as follows. The availability factor AF is the total time of actual operation divided by total time in a year. Okay. And the power operating factor, this is also called the capacity factor, okay, which is also often known as the capacity factor, is the total electrical energy generated by the rated capacity of that power plant into the total time in a year. Okay. So this is called the power operating factor or capacity factor. Now let us understand these concepts and let us look back into these types of electrical demand. Now a grid basically collects electrical energy that is being generated by multiple power plants. Alright. Now in each of these cases, we can see, for example, in the summer months, around 2500 megawatts is the minimum electricity demand over the entire 24-hour period, whether it's a weekday or a weekend. Similarly, during the winter months, 2000 megawatts is the minimum electricity demand that is always needed over the entire time over a 24-hour period. So, this much electricity has to be always be there in the grid, and there are certain power plants which are designated to cater to this minimum electricity demand that is always required over a 24-hour day period. So these power plants will run 24/7 to cumulatively generate this base load, which is called the base load power plants. This base load that is always required from the grid. Over and above this is the variation and the increase in the peak loads. Okay, so these are basically power plants that have to be switched on and off during the course of the day to cater to the variability in the demand over and above this base load. Okay, so based on this criteria, we can separate out power plants into the following classifications. So types of power plants based on load role in the power grid. So the first is the base load base load power plant. So these are large power plants of the order of 200 to 1300 megawatt rated capacity. These are also usually very efficient power plants that produce electricity at a low cost when operated continuously near their rated capacity. So these are extremely efficient power plants which are usually operated continuously at their rated capacity because they are extremely efficient when they are run in this constant mode over over days and months at their rated capacity. Extremely efficient power plants. So typically coal and nuclear power plants that operate with the Rankine steam cycle. So these base load power plants are highly efficient, continuously running at constant rated capacity power plants with large capacity of 200 to 1300 megawatts, and are usually in the traditional system. These are basically large scale coal and nuclear power plants that are operating with the Rankine steam power cycle. Usually their availability factor is greater than 90%, and the power operating factor or capacity factor is of the order of 70% to 100%. These are base load power plants. Okay. So one of the characteristics of the base load power plant is they can be run at the rated capacity for extremely long periods of time at a very efficient manner. And this is something that is a concern for renewable energy grids, because this kind of characteristics is hard to come by from usual renewable energy sources. And this is something that we will discuss later in the class. The next type of power plant is called cycling plants or intermediate load plants. Okay. So these are designed to be taken offline and online relatively often. Okay. So these are power plants which are beginning to cater to the variable load that is present in the grid, and hence they can be turned off or turned on relatively often. Okay. These are a mix of older, less efficient steam power plants, hydroelectric power plants, more efficient medium capacity gas power plants. So in the traditional grid, these cycling plants are basically a mix of less efficient older steam power plants, because they are being turned on and off often, their efficiency is going to be low anyways. So the older steam coal power plants are usually put into this mix. Okay. Then hydroelectric power plants, which can be turned off and on very quickly without a significant hit in their efficiency, also cater to this cycling power plant or intermediate load power plant section. Then you have more efficient gas power plants, natural gas power plants, which are also can be turned off and on relatively quickly compared to say coal and nuclear power plants. These are also part of the cyclic plant or intermediate load plant population. So these typically operate during high demand periods, day and early evening, and switch off at late nights when we have low demand. For these, the availability factor is around 60%. So 60% of the time they are on, rest of the time they are switched off. And the power operating factor or capacity factor varies from 25% to 70%. Okay. So both their availability factor and POFs are lower than the base load power plants. The third type of power plants are peak load or peaking power plants. So these are small units, 5 to 120 megawatts, that come online and offline in relatively high frequency to cater to demand spikes. So, while the average can be catered to by the cycling and the base load power plant, on a day-to-day basis there will be sudden spikes in the electricity demand. During a peak time, suddenly there is a lot of units turning on at the same time, that will create a sudden peak demand periods. Okay. So these rapid peaks in demand are the times when these peak load or peaking power plants are turned on. So they have to be more responsive. So have to have the ability to turn off and on in quick time to respond to demand fluctuations. Okay. So these are usually small scale gas and diesel power plants. They have higher cost and lower efficiency. So the cost of electricity production through these small scale power plants are usually high and they have lower efficiency, but the focus here is not to increase efficiency but to increase responsiveness to demand spikes. Okay. So their availability factor is usually less than 20% and their power operating factor is of the order of 5 to 25%. So these are turned on and off relatively frequently, but most of the times they are basically idling. So we will stop here today. We will continue this discussion in the next class and we will see how addition of renewables can create specific challenges to the traditional grid and how certain technologies like energy storage technologies has the capability of overcoming those challenges and successfully adding renewable energy systems to the next generation grid infrastructure. So thank you for listening and we will meet again in the next class. Thank you.